Hello, this is my demonstration video for my ENGPHYS 2E04 design project, which was to design and build a circuit that uses a 7-segment display to cycle through my student number using sequential logic design. Now the first step in the analytical process would be to encode my student number in binary and look for any simplifications. As you can see, there is no 8 or 9, so the most significant bit is always 0 and can just be connected to ground. Secondly, the numbers 0 and 7 are repeated, so 2 flip-flops would be needed to act as counters for those digits. Therefore, in total, 3 flip-flops are required for the inputs to the decoder, and 2 would be to count 0 and 7. I've decided to assign the counter outputs for the non-repeated digits as don't cares so that the finite state machine can be more robust and transition from any initial state. So here is the state transition table for the finite state machine. The second step would be to determine the J and K inputs that allow these state transitions to occur. To do that, the excitation table for JK flip-flop is used, and J1 through J5 and K1 through K5 are determined here. The next step would be to determine the Boolean expression for each input, and to do that, a K-map of each input is used to determine the product of sums and sum of products. And after all of that, I summarize the logic in this table by selecting the simplest Boolean expressions as well as the ones with the most repeated terms seen in the color code in here. I then tallied the number of AND and OR gates required to ensure that the finite state machine is as simple as possible. I also compared each expression to its NAND and NOR equivalent, but that resulted in more complicated expressions and more logic gates used, so I decided to go with the original expression. Note, however, that the JK flip-flops in Multisim Live have inputs of J and K, while the flip-flops used in the lab have inputs of J and not K. So I repeated the above process for not K1, not K2, not K3, not K4, not K5 to use for the physical circuit, which just resulted in 2 more AND gates. Now on to the multisim. So I used the expressions from table 15 to construct and simulate the circuit in multisim, and I also tried to make the layout as simple and straightforward as possible, where the top 3 flip-flops are Q1, Q2, and Q3, and the bottom 2 flip-flops are the counters. Now here is a video of the simulation working. From the simulation, a timing diagram was then generated that shows the state transitions for each rising clock pulse. Now finally onto the physical circuit. So using the expressions from table 16, which resulted in a total of 10 AND gates and 6 OR gates, I built the circuit. Now I know that the wires aren't properly color coded, but I did try to lay out the components in a way that would be easy to visualize. So the top 3 flip-flops are Q1, Q2, and Q3 that goes to the decoder, and the bottom 2 flip-flops are the counters, as well as on the logic gate ICs, the top gates are the ones that goes to J and K, and the bottom ones would just be the ones that helped in building the expression. Now this is a video of it working. Just some concluding remarks. Overall, this project was a great experience as it allowed me to build on all the knowledge taught throughout this course. And although assembling the physical circuit was a bit challenging due to its complexity, I followed some practices such as testing all of the components on the breadboard before assembling and ensuring each wire was in the right pin and also testing the sequence on LEDs before connecting it to the decoder to ensure that I was doing it right throughout the process. And in the end, successfully getting the right output was very satisfying. So thanks for watching.